Have you ever wished you could just peek into the future, or maybe test out a really wild idea without any of the real-world risk? Well, what if you could build a virtual copy of pretty much anything? A car, a factory, even the weather, just to see how it ticks. That's the incredible power of simulation. And today, we're going to break down how these virtual worlds are helping us understand and improve our own.
So here's our game plan. We'll start with a super clear definition, then get into the why we do this in the first place. After that, we've got two big showcases packed with real-world examples, everything from 3D printing to training self-driving cars. And then we'll wrap it all up with the big takeaway. Sound good? Let's dive in.
All right, section 1. Let's start with the absolute basics. What exactly is a simulation? At its core, simulation is really just about creating a digital copy of something real. You can think of it like a virtual blueprint or what a lot of people call a digital twin. It could be a product, a factory floor, you name it. The whole point is to build this safe, virtual sandbox where we can test things, poke them, prod them, and just see what happens, without any of the real-world consequences.
Okay, so we know what it is, but why bother? Why go through all the trouble of building these complex virtual worlds? That's what we're digging into here in Section 2, the core purpose.
Even though the uses for simulation are incredibly diverse, when you really look at the research, the main goal almost always boils down to one of these four things. You're either analyzing a process, designing a control system, planning out some infrastructure, or trying to optimize performance. That's pretty much the fundamental toolkit simulation gives you. All right, enough theory. Let's get into some real, concrete examples. In our first showcase, we're looking at how we simulate tangible, physical stuff. Objects you can actually hold and touch. And what's so cool here is the incredible range of scale we're talking about. On one hand, engineers can use something called the finite element method, which is basically a fancy way of breaking a big object into millions of tiny, simple pieces to see the microscopic stress on a single wooden joint. But on the other hand, they can simulate the entire structure of a new material or predict exactly how metal is going to melt and fuse inside a 3D printer. It's like being able to see both the atoms and the final assembly.
And this is not just some academic exercise, right? These virtual tests have very, very real consequences. They're helping us create stronger, lighter materials for things like cars and airplanes. They prevent super expensive mistakes, like a multi-million-dollar manufacturing tool crashing into a part. It's all about getting it right in the digital world before you ever spend a dime in the physical one.
So that's the physical world of individual objects. But what happens when we level up, when we go from simulating a single thing to simulating the complex, interconnected systems that run our world? Let's jump into our second showcase. Okay, let's start with a factory. Instead of just guessing what's causing delays, companies can run simulations of thousands of virtual shifts. This lets them pinpoint the one machine that's slowing everything down, the bottleneck, and fix it to make the whole production line run smoother. Now, let's zoom way, way out to the entire globe. By modeling the unbelievably complex web of global shipping, analysts can see how a single storm in the Pacific or one delayed port can cause a massive ripple effect, impacting when a product gets made on a totally different continent. Now, let's bring it right back into our own homes. People use tools like Cisco Packet Tracer to simulate how all your different smart devices, your lights, your speakers, your thermostat, talk to each other, making sure they actually work together without any glitches. And finally, think about our infrastructure. Traffic simulators are used all the time to test different speed limits or ramp designs to prevent traffic jams in critical spots like tunnels, long before a single car ever drives through. But honestly, the applications get even more creative and way more unexpected. Like this quote says, it's not just for the obvious stuff. The research out there is just full of these fascinating out-of-the-box examples. For instance, simulations are used to design better ventilation systems in poultry houses, which leads to healthier chickens. They let the AI for self-driving cars practice on super dangerous icy roads, where crashing is totally free and the learning is super fast. Scientists use them to update the digital twin of a satellite that's already in orbit with real-time data. They even create virtual hurricanes to train ship captains. The versatility is just mind-blowing. So we've looked at simulations of tiny wood fibers and global supply chains, of smart homes and spaceships. Let's pull all this together now in our final section and look at the big picture.
Across every single one of these fields, from a chicken coop to a spaceship, simulation gives us three fundamental powers. The power to analyze the present in incredible detail, the power to predict how a system is going to behave in the future, and, most importantly, the power to optimize it to get a much better outcome. So, if you remember one thing, it should be this. Simulation gives us an incredibly powerful, low-risk way to innovate. It lets us test and fail and learn and improve our ideas in a virtual space before we ever spend a single dollar or commit a single piece of equipment in the real world. It's really all about making smarter, more informed decisions. So, I'll leave you with this question to think about. If you could create a perfect virtual model of absolutely any system, what would you choose to improve? Thanks so much for tuning in.